A very good day to all of you. In this class, we will discuss all the questions that have come from electronics devices and circuits, that is EDC, in 2021 GATE examination from electronics and telecommunication branch. Okay. So if you see, there are total 3 questions, right? 2 are of 1 mark and 1 is of 2 marks. So there are total 4 mark questions, okay, that have come from this particular subject. Okay. If you see, you may think that the weightage of the subject is less. Okay. But I could see the questions are little tricky. Okay. If you solve tricky and little difficult questions, that will determine the rank. Okay. So you should not concentrate on weightage. You have to solve all the questions in the exam. Okay. So the first question is, a bar of silicon is doped with boron concentration of 10 power of minus 16 per centimeter cube. Okay. So, and assume it to be fully ionized. Okay. What is the meaning? A intrinsic semiconductor. Okay. When it is doped with boron impurity. Okay. It will behave like a p-type semiconductor. Okay. So in this semiconductor, since the concentration of boron, okay, boron concentration is 10 power of 16 per cm cube. Okay. And all are ionized. What is the meaning of fully ionized? Each boron atom, okay, gave one hole to the valence band of the semiconductor. That means the whole concentration, okay, is approximately equal to 10 power of 16 per cm cube. Okay, or it's called concentration of hole is P is 10 power of 16 per cm cube. Okay, so it is exposed to light such that electron hole pairs are generated throughout the volume of the bar. Okay, at a rate of 10 power 20 cm cube per second. Okay, so thing is, if we will expose light to a semiconductor, okay, what will happen when the energy of the bombarding light is more than the band gap of the semiconductor? What it will do? It will break the bond and electron hole pair will generate. Okay, and the rate of generation is given G is equal to how much, guys? 10 power of 20, okay, per cm cube per second, right? And the lifetime is nothing but tau. Okay, lifetime is 100 microsecond. What is lifetime, guys? When electron pair generated, okay, they stay approximately 100 microsecond in the semiconductor before they recombine. Okay, and the intrinsic silicon concentration is nothing but Ni is equal to 10 power of 10 per cm cube, right? Assuming 100% ionization of boron, already we have assumed, right? Because it is 100% ionized, each boron atom gave one hole to the valence band. So the concentration of hole in my semiconductor is 10 power 16 per cm cube, right? It is asking to calculate the approximate product of steady state electron and hole concentration due to this light exposure. Okay, so let us solve this question. Okay, first thing is, to a bar of intrinsic semiconductor, okay, they have doped with boron. Okay, then before doping, okay, before doping, I have the intrinsic semiconductor, right? Intrinsic without any doping. Okay, intrinsic Ni. Okay, so they have given in the intrinsic semiconductor. Okay, the carriers are generated due to mostly thermal energy. Okay, so it is given intrinsic concentration, nothing but electron concentration, nothing but holes concentration is equal to given 10 power of 10 for cm cube. Okay, so now since it is doped with 10 power of 16 number of for cm boron, okay, what will happen? Each boron is ionized. That means each boron have given one hole to the valence band. So the whole concentration, okay, whole concentration, nothing but P, okay, will become now 10 power of 16 for cm3. Okay, so since after doping, okay, the whole concentration become 10 power 16 per cm3. We know there is a law called mass action law. What is mass action law? It is says the concentration of electron in intrinsic semiconductor, okay, into the concentration of holes in intrinsic semiconductor, okay, is equal to same and both are in a square. Okay. Also it says if you take any semiconductor, whether it is doped or undoped, the concentration of electron into the concentration of hole also become the concentration of carriers square in intrinsic semiconductor. Okay, this is called mass action law, right? So using this, what is n now? N is equal to ni square divided by p. So what is ni? Ni is already given 10 power 10, 10 power 10 square divided by p. P is how much? 10 power of 16. This implies is equal to will get 10 power of 4 for cm cube number of electron. Okay, so the summary is after doping, okay, with boron, I got 10 power 16 per cm cube number of holes and 10 power 4 per cm cube number of electrons. Okay, how I calculated? From the mass action law. This is called mass action law. You might have studied that action law. Okay, so now what happened? First, initially it was intrinsic. Now we dope. Now what are you doing? To the doped semiconductor, I am exposing to the light. Okay, when I expose to the light, since the bombarded light energy is more than the band energy, it will break the bond and it will generate carriers. Okay, so the carrier generation is nothing but G is 10 power of 12, 20 per cm cube per second. Okay, so the after exposing, okay, what is the number of electron generated or hole generated? So number of electron generated and hole generated is electron per hole generated is equal to G into tau. Nothing but the generation rate into lifetime. Okay, what is generation rate? 10 power of 20 into lifetime is how much? 100 microsecond. 100 into 10 power of minus 6. Okay, is equal to 10 power of 16. Okay, per cm cube. Okay, so what happened? There were 16 number of holes, then the 4 number of electrons. Now this much number of electrons and holes generated. Okay, so the total number of hole P total is equal to, already I have 10 power 16, okay, number of holes per centimeter cube, plus again I have generated 10 power 16 holes per cm cube. So it equal to 2 into 10 power of 16 per cm cube. Okay, now the electron total will be equal to, already I have 10 power 4 per cm cube from the doping. Okay, 10 power 4 already I have from doping, plus again I have generated, okay, the electron and hole generated in pair, okay, generated 10 power 16 number of electrons, right? Electrons approximately equal to 10 power 4 plus 10 power 16 is equal to 10 power 16 only, right? Approximately 10 power 16 only MQ. Okay, so now I want to calculate the P total into N total is equal to 2 into 10 power of 16 into 10 power of 16 is equal to 2 into 10 power of 32 for CMQ. This is the answer. Okay, so answer is option D. Okay, see again I am summarizing. To a intrinsic, so when the semiconductor was intrinsic, the number of electron and number of holes were 10 power 10 per CMQ. After it is doped, okay, what will happen? The hole concentration will increase to 10 power of 16 per CMQ, and according to mass action law, the electron concentration will decrease to 10 power 4 CMQ per CMQ. Okay, now when you expose to light, electron hole pair will generate, okay, and the electron hole pair generated concentration is equal to the generation rate into the lifetime, nothing but 10 power of 16 per CMQ electrons and holes. So the total holes will be already how much holes were there. Now it is generated by the already generated this much. Okay, so I have to add already how much it was there and how much it is generated. Okay, so like this I have to calculate the total concentration of holes, the total concentration of electrons. Okay, so now I have to calculate concentration of holes into concentration of electrons. It will give me 10 power 22 into 10 power 32 per CMQ. Okay, so this is the answer. Let's move to the next question. So the next question is, you see, there is a good question actually. What it is asking, okay, the energy band diagram, okay, of a p-type semiconductor bar of length L. Okay, the length is L. Okay, what is a p-type semiconductor? When a intrinsic semiconductor is doped with acceptor into impurity, okay, like in the last question it is boron, okay, we'll get p-type semiconductor. Okay, and the valence band EB is sloped, okay, sloped, since the doping is non-uniform, okay, along the bar. So we have to understand, when doping is non-uniform, okay, there will be a band bending, okay, of the valence band. Okay, and the difference between energy levels of the valence band at two edges is del. So at the length 0 it is 0 something, and at L it is something. The difference is del. Okay, so I have to calculate the electric field developed inside the semiconductor bar. Okay, so first try to understand the question. Okay, thing is, see, since first you try to know what is a hole concentration in a p-type semiconductor. Okay, it is equal to NV into exponential of minus EB minus EF by KT. Okay, and you see, the NV is nothing but, it's called effective, okay, density of states. Already might have studied, right? So here you see the whole concentration is depend upon the difference between valence band and the Fermi level, right? And since it is non-uniform, okay, so since the difference between valence band and Fermi level is deciding the concentration, and since it is giving a non-uniform doping, so definitely there will be some difference between, so the difference between EF and EB will not be same, so it is varying according to the given diagram. Okay, So it is varying means the concentration also is varying from this end to this end, and in this end the concentration is low because EF minus EB is more. EF minus EB is more means my concentration is low, and in this end the EF minus EB is very small, so the concentration is more. Okay, so how I represent, you see, this is 0, this is L. Okay, so this is a P type semiconductor of non-uniform doping. Okay, so you see this one, these were the boron or acceptor atoms. Okay, it is saying that it is fully ionized, right? So you see, doping is so that towards this end, okay, toward this end, there are concentration of holes are more, and from here to here, the concentration goes on decreasing. Okay, and you can see for every hole, these are the holes. Okay, these are the holes. So every hole there is a big atom. This is nothing but acceptor atom. Okay, so each acceptor atom that is doped have given one hole to the valence band. So for each acceptor atom, these are big atoms are acceptor atom. There is a hole. Okay, what will happen? You see, when a semiconductor will be doped like this, okay, you could see in this end, okay, the concentration of holes are more, right? The concentration of holes are more, right or not? So since the concentration of holes are more, what will happen, guys? Naturally, the holes will try to move from the higher concentration to lower concentration like this, right? You see how it will move. You see the concentration will move. Okay, so when the holes will move, okay, so see before it was electrically neutral, this region, okay, because for every bounded acceptor atom there is a hole. Okay, after it moved, okay, you could see in this region, okay, in this region there is net negative charge, and in this region there is net positive charge. Okay, so what will happen? Since the holes moved from region 2 to region 1 due to concentration gradient, okay, the acceptor atom got exposed and I got net negative charge, okay, and net positive charge in region 1, okay, because here holes are more, okay, so it will create one electric field. Okay, see, this electric field will be created because here net positive charge is there, here net negative charge is there, so electric field is created. What will happen? This created electric field, okay, this created electric field because of movement of holes due to concentration gradient, okay, will expose the bounded atoms, and there will be a net negative charge in region 2, there will be net positive charge in region 1. So since there is a net charge, there will be a built-in electric field. This electric field is created inside because of the charge separation. Okay, what will happen? This electric field will try to oppose the further motion of holes from region 2 to region 1. Okay, but initially the opposition force due to electric field is less compared to the concentration gradient force. So what will happen? Again, further they will move. Okay, further they will move. Okay, they will move. And what will happen? Again, I have negative charges that is exposed. Here I got more positive charge. So what will happen? The electric field again will increase. Okay, it have an increase. See, this electric field got increased. Then electric field increase. What will happen? This process will keep continue until the opposition force due to the built-in electric field is equal to the concentration gradient force. In steady state, what will happen? There will be no net motion of charge. Net, okay, motion of holes, because the built-in electric field is opposing the motion, so the net current will be equal to 0. Okay, understand? So the built-in electric field is created due to non-uniform doping that cause the movement of holes in the semiconductor bar, which created the built-in electric field, because in steady state the built-in electric field opposition force is equal to the concentration gradient force. There will be no net motion of holes in the semiconductor, and the net current equal to 0. Okay, so I want to give you understanding of how electric field is getting created. Now we have to compute the electric field created due to the concentration gradient. Okay, so let us compute. Okay, since I said, okay, the current is 0. Okay, the current is equal to 0. Right or not? What is the current, guys? The whole current is nothing but, in a semiconductor, it is consisting of drift plus diffusion. Okay, nothing but the drift current is, so I am writing, okay, current due to drift plus current due to drift okay, drift plus current due to diffusion is equal to 0. Okay, this implies, what is the current, guys? Current is nothing but, you know, charge into concentration of holes into the mobility of holes into the electric field. Okay, that is created, plus charge into diffusion constant into concentration gradient is equal to 0. Okay, so this implies, okay, what will happen, guys? You see, if you see electric field equal to minus, okay, dp by mu p okay, into 1 by p into dp by dx. Okay, this is a important equation. Okay, now you see, minus, what is dp by mu p? We know is thermal voltage Vt, nothing but Vt is equal to, what is Vt? Vt is equal to Kt by Q. Okay, so already you know dp by mu p is equal to thermal voltage Vt into 1 by p into dp by dx. Okay, now you calculate what is minus Vt by p into d by dx of, what is p? P is nothing but, already I mentioned, okay, P is nv into exponential of this one, right? So nv into exponential of minus ev minus ef by kt, right? So if I have to derivative it, okay, how much I will get? Minus Vt by p. So derivative of exponential is again exponential. Okay, so nv into exponential of minus ev, right, ev minus ef by kt, okay, into d by dx of, okay, minus eb minus ef. Okay, now since this quantity, okay, we know is nothing but p, right? Is nothing but p only. So p get cancel, so I'll get Vt into minus d eb by dx plus d ef by dx, right? Since the formula value is constant, so df by dx is equal to 0. So This implies what you will get E is equal to minus Vt, okay, into minus dEv by dx. What is dEv by dx? Slope is how much? dEv by dx is 0 to L is the length and the height is del. So it is del by L. Okay. So minus del by L. Okay. So L. So I think there is Kt is there, right? By Kt. Okay. So here by Kt. Okay. Into 1 by Kt. Okay. And Vt is equal Kt by Q and Kt get cancel. So I got del by Q and L. Okay. So this is my built-in electric field created. Okay. You see how I have done? Since the current is 0, I have from there I get electric field. Then electric field I have differentiated. Okay. So if I do a differentiation of this, I will get divide exponential again differentiation of the inside term. Okay. The differentiation of the inside term will give me the Kt will come outside. Kt have come outside. Okay. Kt have come outside. Then dEv by dx is nothing but del by L. I put del by L. And df by dx is 0 because it is constant. Okay. So if I put all these things, I got the answer del by L. Okay. So little this is little tricky question. Okay. So now go to the next question. Okay, guys. In a silicon PN junction, okay, and in the figure, the doping of P region is this. Okay, that means doping of P region means acceptor atom. Okay, is equal to 10 power of so 5 into 10 power of 16 per cm cube. Okay, and doping in N region is nothing but donor atom. Nd is equal to 10 into 10 power of 16 per cm cube. Okay, and what is given? VBI. This is VBI. Built-in electric field given. Charge is given. Okay, permittivity is given. Okay, what it is asking? The magnitude of reverse bias voltage that would completely deplete one of the two regions. That means we have to calculate the magnitude of reverse bias. Okay, reverse bias. Okay, that will deplete either N or P region. Okay, which of any of the two. Okay, see guys, already we know. Okay, there will be some built-in electric field. So if I see the semiconductor here, let me draw here. I have space. Okay, I have space. Okay, so if you see a semiconductor, this is P type, this is N type. Okay, there will be some built-in electric field. Electric field. This is called depletion width. Width. So before I apply anything, there is a built-in electric field and built-in depletion width, that is called W. Okay, in the semiconductor. Okay, what will happen when I connect a reverse bias, right? What will happen? The depletion width will widen. Okay, how it widen? We already know the theory, right? Okay, what will happen? When I go on increasing this VR, what will happen? This will widen. Okay, suppose VR1. Okay, now if I apply VR2, which is greater than VR1, okay, what will happen? Again, it will widen. Widen. Okay, what will happen? If I keep increasing the reverse bias potential, okay, what will happen? A time will come, either the N region or the P region will completely deplete. Okay, so that potential I need to calculate at which either P side or N side will deplete completely. Okay, so this is the question. So guys, we know, okay, we know the depletion width in a semiconductor W is nothing but how much, guys? Can you tell me? It is depletion width in, and see, the depletion width consists of some from the P region is called XP, okay, and some from the N region is called XN, okay. So the depletion width is nothing but sum of P region depletion width and N region depletion width, okay. So it's XP plus XN, okay, is equal to root over of 2 epsilon VBI by Q. Epsilon is permittivity is nothing but epsilon 0 into epsilon silicon, okay. The epsilon is nothing but epsilon 0 into epsilon silicon, okay, into the VBI into, okay, plus the reverse charge potential, okay, into 1 by Na plus 1 by Nd, okay. This is the total width, okay. And also we know the total charge in N side that is exposed and the total charge in P side that is exposed are same, okay. So that will give me total charge in P side is nothing but Na into XP into area. Area is towards the into the board, okay, the total area, okay, that is the area, okay, is equal to the width in N region is nothing but number of dopants into depletion width is Xn into area, okay. Simplifies Na into XP is equal to Nd into Xn. Simplifies XP by Xn is equal to how much? Nd by Na, okay. What is given here? Nd is nothing but 10 into 10 to the 16, okay, and Na is nothing but 5 into 10 to the 16, okay. So 10 into 10 power of 16 divided by 5 into 10 power of 16 is equal to 2, okay. Simplifies XP is equal to 2 times Xn, right? Right. So in this case, see which will deplete first. Since the N side is, we will see which will deplete first, okay. Let N side will be deplete first, okay. So let N side will deplete first. What will happen? Then Xn will be equal to how much? 0.2 micrometer, right? 0.2 micrometer. In that case, what will be XP? XP is equal to 2 into Xn, it will be 0.4 micrometer. So completely it will deplete, then it will deplete up to 0.4 micrometer, okay. So what it will give? The total width of depletion region will be Xn plus XP is equal to 0.2 plus 0.4 is equal to 0.6 micrometer, okay. So what I am calculating, when I go on increasing the reverse bias potential, the depletion width will move, and it will try to reach the edge, okay. At that point, the total depletion width in N side is 0.2 micrometer and the total depletion region in P side is 0.4 micrometer, okay. So the total width is equal to Xn plus XP is equal to 0.6 micrometer, okay. I have to calculate at what potential of reverse bias this will happen, okay. We put everything in the equation. W is equal to 0.6 micrometer, okay, is equal to root over of 2 into epsilon is epsilon 0 into epsilon silicon, nothing but 8.85 into 10 power of minus 12 farad per meter or minus 14 farad per cm into what is epsilon silicon is 12. Okay, into VBI plus VR. What is VBI? VBI is given 0.8 volt plus VR, right? Divided by Q. Charge is given 1.6 into 10 power of minus 19. Okay, into 1 by Na. Na is how much, guys? Na is 510 per 10 plus 1 by Nd. Nd is how much? 10 into 10 power of 16. Okay, so in this equation you see everything is known, only I have to calculate VR. Okay, so use your calculator and solve. If you solve using calculator, how much you will get? If you solve, so let us see how much we will get. We will get around 8.2395 volt. Okay, so if you solve this equation, okay, we will get here is equal to 8.2395 volt. So the answer is 8.2395 volt. Okay, so this is the last question. Okay, so you see, since the questions are a little tricky, okay, if you solve in the examination, that will definitely determine your rank. Okay, so the more difficult question you will solve, the better rank you will get. Okay, so easy questions everyone will solve, but tricky questions will be solved by only the good rankers. Okay, so that's all. Thank you guys, all of you.